Okay, we proceed more with vectors, and first of all, say I have two vectors which are in opposite directions and they have the same magnitude. So I add vectors in opposite directions. Basically, I have to add vector A with the vector minus B. Okay. And since they have the same magnitude, so ultimately what I get is a vector whose magnitude is 0. Such a vector, and obviously it has no specific direction. Such a vector we call zero vector or a null vector. Okay. There's another kind of vector. A vector whose length is 1, magnitude is 1. It's called a unit vector. Now there are some standard unit vectors. A unit vector along positive x-axis is labeled by I, and unit vectors are always written with a cap, I cap or I hat. A unit vector along the y-axis, positive y-axis, is labeled as J, J cap or J hat, and a unit vector along positive z-axis is labeled as K hat or a K cap. Now any vector divided by its length or magnitude will give a vector of length 1. Unit vector. In the same direction as this, or we said parallel to this. So any vector can therefore be written as the unit vector in that direction multiplied by its magnitude is the unit vector. Now we come to the concept of again vector addition. We learned that we can add vectors geometrically by triangle law or parallelogram law, and the analytical method we learned. Now it becomes, this kind of vector addition is actually quite tedious, and the reason being that if I have a large number of vectors which I have to add, say 5 vectors, 7 vectors, 8 vectors, 9, 10, then this geometrical method becomes very tedious. So there exists a neater and easier technique, and that technique is to draw a vector along the xy coordinate axis and resolve it into vectors along the x-axis and y-axis. Now suppose this is the xy coordinate system and I have a vector which is in this direction. I translate the vector parallel to itself. Now when a vector is translated parallel to itself, it remains the same because I have not changed its length nor its direction. So the vector remains the same. So I translate it parallel to itself and draw it from the origin of the xy coordinate system. Then I draw a perpendicular on the x-axis. So I can say that this vector is basically the vector sum of a vector along the x-axis plus a vector along the y-axis. So a person moving in this direction and then moving in this direction is the same as person moving from here to here. So this is basically the vector sum of this vector along x-axis plus this vector along the y-axis. So we write it like this. Vector A is the resultant of AX vector plus AY vector. Now we just now learnt about unit vectors. So the vector AX can be written as I hat. Remember, I hat was unit vector along the x-axis into length of AX. And similarly, AY vector can be written as J hat into length of AY. So vector A can be written as IAX plus JAY. Now how do I find the length of AX? This is a right angle triangle. Cos theta is AX upon A. So AX is A cos theta. And similarly, sin theta is AY upon A. Now this AY I can also draw along this vector translated parallel to itself, remains unchanged. So ay can be written as a sine theta. And so a is, or a square you can say, is equal to ax square plus ay square because it's a right angle triangle. These are the magnitudes. And tan theta, the direction, is ay upon ax. Now what is the use? And okay, in 3 dimensions I can write it like this, and this is the magnitude of a vector in 3 dimensions. Now what's the use of these components? The use is that if I had several vectors and I resolve them into the x and y components, then the x components are all lying along the same direction, same line. Y components are all lying along the same direction or same line. So vectors along the same line can be added like scalars, so I can add them. Vectors along the same line can be added like scalars, so I add them. So I can add all the x components of the vectors and get some resultant x component. I can also add all the y components of all the vectors and get a resultant y component. So I have a resultant x component and a resultant y component, which I'm showing over here. If say there's a vector r equals a plus b, then rx, x component of the resultant, will be sum of the x components of these two. Ry, y component of resultant, sum of these two. Rz will be this. So the vector r is this. So I just add the x components to get the resultant x component. I add the y components to get the resultant y. And I add the z components to get the resultant z component of the resultant vector. And then this is the magnitude of the resultant. And the same rule applies if you are to subtract two vectors. The same rule will apply for addition and subtraction of vectors. So this is the use of components of a vector. And of course there will be many more uses which we shall study further on.